Okay, thank you. Yes, I should thank the organizer for this very lively program, which I've been attending this week. So yes, they asked me to talk about non-Gaussianity in warm inflation. Um, I have prepared something a bit more general because Marco told me that maybe there weren't many talks on inflation, so I thought maybe I mention some general things because warm inflation is a subclass of inflationary models. So I make some more general comments and then focus in the second half of the talk on warm inflation. But however, then it might be a bit boring at the beginning because it's very general. So, okay. Anyway, so introduction is that I always start from this diagram. So inflation is the theory of initial condition. So if we draw this conformal diagram and then put ourselves here, and then in hot Big Bang cosmology, we have a Big Bang singularity. And then we see things which might seem a bit puzzling, like we see CMB, and we see galaxies, and they are very homogeneous. The universe that we see is very homogeneous, but in Big Bang cosmology, we see things that have not been in causal contact with each other. If we go all the way back to the Big Bang singularity, and this looks puzzling, and inflation was a way to resolve this puzzle and some other puzzles like curvature problem and so on. So inflation is essentially an extension of the hot Big Bang cosmology to the past. So one can think of it as a theory of the initial condition for the late cosmology. And it can be realized using a very simple particle physics model, the scalar field coupled to gravity. With a sufficiently flat potential, and this scalar field should be rolling down the potential. Of course, then there are alternatives to these simple models that produce some distinct signatures that one might discover using the observation. Now, so what is so, of course, one interesting feature of inflation is that it was introduced to solve some problems about the background, like homogeneity or the spatial curvature, flatness of the universe, or absence of monopoles. But then it turned out to be a beautiful theory of cosmological perturbation that creates cosmological fluctuations from quantum 0-point fluctuations of this scalar field. Another one important point about inflation is that it has this model that I'm saying, or some other alternatives that realize inflation, they are necessarily beyond the standard model physics. So inflation needs BSM, and therefore the signatures of this beyond the standard model physics can be imprinted during this process of promoting quantum fluctuations into cosmological perturbations. The signatures of this can be imprinted into this cosmological fluctuation. So here is the workshop about new physics. So here is the new physics, and then cosmological fluctuations are measured using galaxy service. So this is all that I have to do with this workshop. Um, Now, right. So there are basically one theme in research regarding inflation is to basically try to find signatures that are realistically observable, or within the near future we can look for them and perhaps rule out those BSM models or find the signature. So that's essentially the name of the game here. Of course, there are other more conceptual questions regarding inflation, and it might turn out that at some point we find that those conceptual questions also leave some imprints that we can look for in the data. But uh, most of them at the moment are just conceptual questions that we want to think about, or people think about, just uh, to try to understand, just based on the consistency, mathematical consistency, or the building a general framework. So for instance, I just mentioned some of them. Like for instance, one conceptual question with inflation is that even though it's a resolution of the Big Bang singularity of the late time cosmology, it is itself not eternal to the past. So therefore, inflation itself has a problem of initial singularity. Although this problem is not a phenomenological problem, in the sense that this initial singularity can be so far in the past that will not affect any observables. So therefore, it's a conceptual problem, not necessarily a phenomenological problem. Or there is the problem of a measure problem, or yeah, these are somehow all interconnected. So there's measure problem, there is the landscape, the choice of the flatness of the inflationary potential. How do we obtain a reasonable scenario that can realize inflation within our range of possibilities, and how do we choose what is the probability measure on these possibilities? Then there is, of course, there is an issue of eternal inflation, which is and that once you have inflation, there is some probability for having eternal inflation, or typically there is a probability of having eternal inflation. And once you have eternal inflation, you populate all possibilities, and then there will be a question of if we can put a likelihood on what say scenario is more likely and what is less likely. Okay, so now, of course, within this mess, there is a possibility of tunneling, and then perhaps you have heard recently that if our universe resulted after Coleman-Deluccia bubble nucleation, then there are some observable signatures that one can look for, like having some negative spatial curvature. Okay, so now coming back to the BSM aspect, let me talk about the energy scales. So here we have highest energy scale, which is we know that there has to be some new physics, 10 to the 19 GeV. Now, in principle, the energy scale of inflation, the frequency of this quantum fluctuation when they turn into cosmological perturbations can be relatively close to this highest energy scale compared to what we do on the Earth. So for now, we only have an upper bound on that energy scale, and that is something of order. So that is Hubble inflation, the curvature scale during inflation, and that could be as high as 14 G or 13 G. Of course, the lower bound is extremely low, is like 10 to the minus 20 eV or so. And we don't really, there is no indication that it has to be sitting very close to this upper bound. Yes. What is said in the upper bound is the tensor modes. So we have here, I mentioned the fact that during inflation, the fluctuations of the inflaton field turn into cosmological fluctuation. They turn into scalar or adiabatic modes that we usually study in cosmological perturbation theory. But of course, there are also tensor modes, and those will also be excited during inflation. And the amplitude of those will be directly related to the curvature scale of inflation. And now, since we have upper bound on the amplitude of tensor modes, let's put an upper bound on this. In fact, let me just write the formula. It's something like H tensor. This is for, let's say, 10 TT. This, the prediction of inflation will be something like of H inflation divided by M prime. Then, of course, we have usually report the answer in terms of the tensor to the scale ratio, and that directly translates into a bound on H inflation. Yes, thanks for asking. Maybe I say a few more words about it once I talk about warm inflation. Or I say, yes, so we have this bound. We hope to measure R. So if we can measure R, it has to be, energy scale of inflation has to be high, maybe a couple of orders of magnitude around this value. Otherwise, we won't see it, but in principle, it can be much lower. Okay, so that's why it's very interesting from the perspective of doing BSM physics, because in principle, we are probing energy scales that we cannot even dream of doing it in collider physics. Okay, so yeah, maybe I can be a bit more specific about phenomenological questions that can be asked. Of course, there could be more. I'm just listing some of the questions that might be asking by measuring cosmological perturbation. So, for instance, we can ask what is the shape of this potential. This perhaps as a subclass of this question, it could be asking about the possibility of a tunneling. So if we have a tunneling, inflation happening after a phase transition or a tunneling, then this potential perhaps should look like this, should have a false minimum, and then there should be tunneling to here and then rolling down. And then if this tunneling happens, if the modes that we observe is not very exit the horizon around this time, then perhaps we can get an idea about this possibility. We can ask about self-interactions of this inflaton field. So for instance, the one important point is that to realize inflation, its potential should be sufficiently flat so that we get accelerated expansion. Like if it's perfectly flat, it's like cosmological constant, which gives us a perfectly accelerating universe with a constant rate of acceleration. It doesn't have to be as flat, but sufficiently flat. That means that interactions are suppressed, and non-derivative interactions are suppressed, but derivative interactions can be large. So for instance, we can look for possibility of having interactions of this scalar field, derivative interactions of the scalar field. We can ask about single versus multi-field inflation. So if in addition to inflaton, there are other light fields that maybe I call them sigma. And then this potential might be not just a valley in one direction, but has a weird shape in this multi-field landscape. And inflation happens by rolling in this multi-dimensional space. We can ask about the possibility of a particle or gravitational wave production during inflation. At some energy scale, which is much higher than the curvature scale. So this would be actually a probe of a high energy scales beyond H inflation during inflation. And then, for instance, one other question that people ask sometimes is the possibility of primordial magnetic field, and so on. Okay, so this is just some possibilities. What have we seen? So far, the only thing that we have seen is the scalar power. Actually, we have only seen two numbers so far. -4. So we have already seen an amplitude and a power for this primordial, the scalar perturbations, where AS is something about the, okay, I shouldn't give very detailed numbers, because they are gonna be probably wrong. NS something like that. Okay, so yeah, we have only seen two numbers, and then we have upper bounds on some other possibilities. What are the other possibilities that we hope to see? One of them is running. It's just deviation of this scalar power from being an exact power law. So let's say DNS D log K. And other is tensor modes that I mentioned, or tensor to scale ratio, R, which is 2PT over PS. And this is currently bounded to be less than 0.4. And then the other important thing is primordial non-Gaussianity, which is supposed to be the main subject of this talk. So PNG. Right, so what is primordial non-Gaussianity is basically the statement that the moment we have, so far, so this power spectrum is obviously just determining the 2-point function. So if it was Gaussian statistics, everything would be determined by this 2-point function. But whenever we have interactions, then the resulting correlation functions will not be Gaussian. There will be necessarily some non-Gaussianities. And there are always interactions because there is at least gravity in this model. Gravitational theory is an interacting theory. So there is a minimal amount of non-Gaussianity in any inflationary model. In general, it's the first place to look at it is the 3-point function. For a Gaussian field, that would be 0, and that we parameterize it usually by expanding it in terms of a template of possible functions. FNLA, FA, and of course this depends on these three functions have three momenta. They have to sum up to zero because of translation symmetry. So they only depend on this shape of the triangle. Also, they can depend on the size, but since we have approximately scale invariant and the spectrum, the dependence on the size is also the small. But okay, at this level, I can just write. Right, so we generally expand this three-point function in terms of a template of possibilities, and then what's it's basically what the way we try to constrain models on inflation or look for signatures of different BSM models is to ask what shapes they predict for this three-point function or higher point correlation functions or other measures of non-Gaussianity and with what amplitude, as usual. And now, okay, there are some motivated, theoretically motivated templates that come from different models. Like, for instance, if I consider then they will generically predict a type of template which is called the non-local. What is it called? A local, not local non-Gaussian. Or derivative interactions in single field. They produce equilateral type non-Gaussianity. So these are different functions that they look very different, so we can distinguish them in the data, and we only have constraints on this. So FNL local or constraint is something like awarded one, a few, and FNL equilateral is something around 50. Now, what is the minimum value that we would expect? Just from gravitational interactions, that's something about the 1 minus ns. So it's about 10 to the minus 2. Is about 2 orders of magnitude below the bounds that we have. And now, in general, of course, it would be good to have realistic targets. That's what I was mentioning earlier. It would be nice to have realistic target for experiments. Of course, this is a very nice target because it's the floor. We should always have it, but it seems a bit unrealistic at the moment. So it would be nice to have models which are motivated and give us larger value. Usually, actually, FNS of order 1 can be motivated in different models. So, for instance, FNL equilateral of order 1 realistic. So FNL equilateral of order 1, it's a realistic target. It's an interesting target because it basically tells us whether this field that we are talking about, it's whether we are seeing the fluctuation of the same fundamental field that derives the background, or whether it's a the fluctuating field is an emergent field like pions that arise from some it's a low energy description of some background that whose fundamental field is something different. So FNA equilateral order 1 is an interesting target. also FNL local of order 1 is an interesting target, even though one cannot really say that there are multi-field models that produce local non-Gaussianity, which is smaller. One cannot say it's going below 1 rules out multi-field. But still, it's a very many models of multi-field inflation can predict this. Okay, so now here I'm gonna talk about warm inflation, partly because it is a realistic target. It is what, as I'm gonna mention, I'm not really going to derive anything for you, but as I'm gonna mention, warm inflation also predicts FNL, non-Gaussianity, with actually distinguishable shapes or distinguishable functions compared to these others, with an amplitude which is something between 1 and 50. So let's call it 1. So it is a reasonable target, and then I want to show that as a BSM model, as a model for deriving inflation seems to be a reasonable model. It has also some conceptual, it has a conceptual differences compared to the minimal model. So it is interesting to be able to identify or rule it out as not only just a model that gives a prediction, but also because it has different conceptual aspects. Okay, so now I'm gonna talk about warm inflation. Of course, feel free to ask questions. Okay, so it's a very old idea. It goes back to 80s, the idea of warm inflation, almost as old as original inflation, by Fang, Mas, Yokoyama, and Maeda. These are all papers in 80s that have the idea of warm inflation. So what is the general idea is to have some mechanism during inflation that introduces friction on the motion of the inflaton field. So you want to transfer energy from inflaton as it rolls down to some other sector and extract energy from inflation. How does it become warm? Because these extra components, they self-interact and thermalize. Okay, so now what is so therefore, let me just write, if we want to extract energy from infant, or maybe I write it late. Let me write, I'll write it late. Uh, right, what are the conceptual or stochastic fluctuations? And then, of course, it comes with the phenomenological novelties, which are that since you have this extra friction, essentially the background model will be different. The background evolution will be different. As a result, given also the source of fluctuations are different. So as a result, given for a fixed V of phi, say m squared phi squared, which now has been ruled out because of the NSR measurements. Now a fixed V of phi has leads to different different NSR predictions. So this is at the level of just background, at the level of determining the potential. And then, of course, it also leads to, as I mentioned here, leads to primordial non-Gaussianity with sizable amplitude and distinguishable shape. Now, one general comment about feasibility of worm inflation is that I want these conditions to be satisfied. So now let me be a little bit more specific. So I want inflaton field phi. Still there is an inflaton and a potential, yes. Do I get a larger running? Not necessarily, no. So running typically is something of order of second order in slow roll parameters. It's the same thing here. But then what is exactly the numerical coefficient depends on the shape of the potential. The order of magnitude is the same, second order in a slow roll parameter. So right, you have, it's a multi-fit model basically. It's not a single fit model. For now, I just write X for that extra sector. And the idea is that if inflaton was not rolling, it was just a cosmological constant. Cosmological constant is a constant, cannot do anything. But if it's rolling, then it can give its energy to this other sector. So therefore, the kinetic energy of inflaton can be dissipated in this other sector in such a way that I satisfy this condition, rho x over rho total. I still want to be inflating, so potential energy has to dominate. As you know, that potential energy of inflaton would act like a cosmological constant, so it gives me W exactly -1, then kinetic energy or radiation will let me to deviate from -1. So we want to be close to -1, which means that this should be of order of epsilon, some sort of a slow roll parameter, and should be much less than 1. At the same time, to call it warm, less than 1, but non-decay, important. Or not exponentially decay. At the same time, we want T Tx, let's say much bigger than H. And these two conditions are actually compatible because this is compatible with rho x, which if they thermalize, it becomes Tx to the 4th, much less than rho total, because rho total is m Planck squared H squared, and these two conditions are compatible because m Planck is much bigger than H. Nice example to keep in mind is that today CMB temperature is much bigger than H naught, but omega CMB is something over 10 to the -5. Okay, so now at the level of a little bit more detail, so we want to see what happens if we realize this, then our background evolution is going to change. So normally, in usual single field slow roll inflation, we have this scalar field which is rolling. And what gives rise to the slow roll is having this Hubble friction term. Now, because of this particle production that I mentioned, these background equations will be modified. So there will be an extra friction term here. And on top of that, there will be a conservation equation for the energy density of this extra sector, which now imagine they thermalize. So the idea is that they have some kind of self-interaction so that they thermalize. So here I'm just writing the conservation equation for a thermal component. However, here on the right-hand side, I'm not going to put 0 because of this fact that it's being sourced by inflat. So here there will be gamma phi dot square. Now, depending on the temperature dependence of gamma, gamma itself is actually depends on the temperature generically. Let's say one motivated dependence will be TQ, as in a model that I'm going to discuss later. So this is one example, or there could be other examples. You can find that this system, now this system, we know that for appropriate shape of the potential has a slow roll attractor. Say I have m squared, phi squared. If I take phi to be super Planckian, then there is a slow roll attractor, and it gives me inflation. If I want 60 EFOs, it's enough to take phi to be 15 m Planck in m squared phi squared. This system, I can see that also has a slow roll attractor. It has, of course, a new parameter in it, which is this gamma. So there is a proportionality coefficient here. One can choose that and see that again for appropriate shape of the potential and field excursion. This system also has a warm slow roll attractor. Oh, yes, in fact, yes. So, of course, so far I didn't talk about the macroscopic realization. Oh, sorry, thank you. Yeah. Right, yes. So this is, I have not talked about the microscopic realization. So if you realize it, then for a good choice of V, there will be, there can be the slow roll attractor. Attractor means that you deviate a bit around that the slow roll solution, and then you come back. Perturbatively, at least one can see that it comes back. Now, of course, then the important question is the realization of this. And let me see. Yes, I'm gonna talk about thermal mass definitely in this slide. But I'll talk about it within this particular model, or after introducing this particular model. So minimal warm inflation is a particular microscopic mechanism to realize this scenario, meaning that it's a microscopic model for what that X is and what that interaction between phi and X is. So in this realization, X is X is taken to be a Young-Mills sector, so non-abelian gauge fields. And then the coupling and phi, the inflaton field is taken to be an axion field, which is coupled to the Young-Mills field via this famous coupling. This G is the field strength of the Young-Mills field. Okay, so now what would be the general effect of introducing this coupling? So so therefore the full Lagrangian is something like we have a scalar field with a potential, and then we add to that potential this coupling to GG tilde. And then, of course, I have also the trace G squared for the Yang. So this is the full model. Is, as I mentioned, it's a multi-field model. Okay, so now if I consider this system, this Yang-Mills sector to be at finite temperature, together with this coupling, then it does two things. One is, or several things. One of them is that it produces a gamma, a friction term, which goes as alpha to the phi. Alpha is the coupling of Yang-Mills. T cubed divided by F squared. This T cubed divided by F squared is just dimensional analysis. So I can easily convince you maybe later that this has to be like that. This alpha to the 5 is the non-trivial factor here. On the other hand, it does some other thing, which is that this coupling also changes the potential for the inflaton. So there is a finite temperature correction to the potential. This is something very generic. There are finite temperature to the potentials because other fields depend on the value of what these other fields are doing depends on the value of phi. So there will be a correction to the potential. In particular, there will be a thermal mass. So thermal mass in a model like this, if I didn't mention, if it coupling was not that, but was a similar dimension 5 coupling, would be something over the T to the 4 over F squared. Again, this is just dimensional analysis. The fact that it should go like that. This 1 over F squared comes from the fact that I have F1 over F here. But it turns out that if this is Yang-Mills, then there will be a suppression which is at the small values of alpha, there will be an exponential suppression of this mass. The origin of this friction term are some processes which are called the sphalerons. And the origin of this mass term are some other processes which are called instants. And then this is the generic suppression that one gets for instantons. Sphalerons, it turns out they are only power law suppressed. So one can see that when alpha is the small, much less than 1, the correction to the thermal mass will be exponentially suppressed, while this gamma will be only power law suppressed. Now, let me mention the general statement that if it was some other microscopic theory, and that was basically the original challenge to Bohr inflation, was that if you write a generic field theory, if it wasn't Yang-Mills, then this exponential suppression wouldn't be here. And then if you consider these two corrections, you see that the thermal mass is much, much more important than the friction. And therefore, you wouldn't be able to realize inflation without fine-tuning this thermal mass, but it really doesn't make much sense to fine-tune the thermal mass because it depends on the temperature. So that's why that was the main criticism to Bohr inflation until very recently, the fact that you would not be able to realize it microscopically because generically you will make a big and unacceptable corrections to the potential. This particular scenario goes around. What about? In what sense? Well, as you know, the correction to the potential is temperature dependent, right? So if you go to zero temperature, the correction, like for instance, the axion mass is the full, yeah, it's the full potential. Oh, the correction to the potential is a function of temperature. It's the usual thing, like you see, the axion at high temperature is effectively massless. As temperature goes down, its potential becomes bigger. T is bigger than lambda Yang-Mills, which is equivalent to saying alpha is small. These two are real. No, this V, the idea is that here, this V of phi has extra contribution to it. So I'm not relying on the thermal contribution of this Yang-Mills to create the V of phi. Think of it as having another Yang-Mills sector. If just in the context of axions, there should be yet another Yang-Mills sector, which is say at zero temperature, and it produces a V of phi. And then this other Yang-Mills is at final temperature, and its correction to the potential is negligible. Okay, so now here I said instant, and let me just mention, yeah. Yeah. Yeah, you know this slow roll parameters are like V double prime over H squared, or yeah, that is right, exactly. Maybe just mention some couple of words about the sphalurons. So sphalurons are some processes a bit similar to instantons, but they are intrinsically finite temperature effects. One can think of them as real-time trajectories that complete the cycle in the field space. That Yang-Mills turns out to have a cycle in its field space, and then the sphalurons are non-perturbative processes that in real time complete that cycle. And that cycle can be completed in two other ways. So these sphalurons have handedness. So I draw them as dots and stars. At finite temperature, they happen randomly here and there. So this, let's say this is a left-handed sphaluron, and this is a right-handed one. And then what happens is that when we have a rolling inflaton field, there will be an imbalance between left-handed and right-handed ones. And every left-handed sphaluron gives some energy to the inflaton, while every right-handed one extracts energy. If there is an imbalance between the two, the net effect would be a friction. No. So yes, so as a result, you will get this extra friction term that goes let's actually say this. Say L left-handed minus N right-handed is proportional to phi dot. Then the amount of energy that you extract is also proportional to phi dot. Therefore, the rate of the energy transfer would be proportional to phi dot square. Okay, so now what I wanted to mention, the important thing, and then we can maybe go to the main point, is that this process of transfer of energy that we have in this model is something that happens microscopically. So these sphalurons are microscopic processes that happen basically at the only scale in this microscopic model, which is the temperature. So they have a size, effective size of a spharon is 1/t. So therefore, this transfer of energy is something that happens locally here and there, and as a result, it leads to fluctuations of the inflat. So this model not only changes the background evolution by introducing that extra friction term, it also changes the fluctuations. Now, a formal way of saying it is that there is a fluctuation dissipation theorem that tells us the moment I want to look at the equation of motion, not for the background, but for the full field, I also have to put a noise term in here whose variance is related to my dissipation coefficient. And it's basically these fluctuations that are produced via this macroscopic model that will be the source of cosmological perturbations in this model. They are much bigger and dominant over quantum 0-point fluctuation. It's kind of obvious, right? If I do something, obviously, I excite the field above the 0-point fluctuations. Now, to study the fluctuations, we remember that we are interested in cosmological perturbations that are associated to, where is this? Are associated to this scale h. So this is the scale of cosmological perturbations when they cross the horizon and they freeze. This is the scale of microphysics. So there is a big hierarchy between those. And therefore, to study cosmological perturbations, one can actually ignore the details of microphysics and write some effective description that is valid at lower energies compared to T. What is that effective description? Is basically a hydrodynamic model for the Yang means. The Yang means at finite temperature is just described by a fluid. At leading order, it is just a radiation fluid. Rho over 3 g mu nu plus higher derivative corrections. And of course, fluid equations are just conservation of this T mu nu. So if I want to study fluctuations, I basically promote this system to a full system for include also perturbations in here, and then instead of just writing the conservation of energy density, I write the full conservation or non-conservation of T mu nu. So basically, the equations that have to be solved for the perturbations are the D'Alembert of phi plus V prime of phi is equal to, here it would be in the underlying model here, I would have need to put alpha over F trace of GG dual. But this we write it in the effective theory as this average on a background of phi, which gives us gamma u mu del mu of phi. U is the forward velocity of this radiation fluid minus, or maybe here there is a minus and here there is a plus, minus a noise field, which are fluctuations on top of that background value. And then the other equation would be the conservation, non-conservation of this T mu nu of Yang means, because there is this source that is coupled, this term that couples the two sectors together. So here I will have something like d mu phi multiplying the same. Okay, this, and in addition, so this xi is a noise. So this is a noise. And its spectrum, its 2-point function is determined by gamma and temperature. So it's basically gamma T. At low frequencies, it's completely fixed by the fluctuation dissipation theory. And gamma T times, say, if it is x and y, it will be delta 4 of x minus 1. Okay, so now, so here, I should say that here I mentioned, I should have said that this model was recently proposed by Berkas, Graham, Kim Berkas, Peter Graham, and David Kaplan. So this is, I think, 2019. This system for the fluctuations in warm inflation, this EFT, was written in much earlier, like in 2012 or something. So it's the usual fact that to write an effective filter, you don't really need to know what is the microscopic realization. Like to write the fluid equation, I don't need to know how the molecular dynamics. So similarly here, if warm inflation can be realized, this would be its effective filter. And it's within this system up to a couple of unknown coefficients that one computes the predictions of the model for cosmological perturbations. What are these predictions? So for instance, I come here. As I mentioned, for a given potential, there will be different predictions for NS and R. So for instance, in this warm inflation model, one can still have, actually, unfortunately, M squared phi squared, this still doesn't work. So perhaps you have seen this NSR plots with contours that look like this. Here is, I think, 0.97. So 1 sigma, 2 sigma, and then there is this line. Okay, anyway, so M squared phi squared, I guess, is here, and then phi to the 4 is probably over there. They are all outside the 2 sigma contour. It turns out that in warm inflation is still M squared phi. Oh, by the way, these are ruled out basically, in particular phi squared, I think ruled out mainly because of predicting too big tensor productions, too large value of R. Instead, in warm inflation, generically, R is very small. Right, R is much, much less than 1. Why? Because there is a big contribution to scalar perturbations, but there isn't, the contribution to tensors are much suppressed compared to that. There is not big anisotropies here to produce tensor perturbations. So R in warm inflation is generically small, but predictions for power law potentials will also differ because the scale perturbations are not the ones that coming from vacuum fluctuations. They are determined by the spectrum of the noise that is fed into this system of perturbations. So the computation for NS and R is essentially 0, but computation for NS has to be redone. It turns out for M squared phi squared, NS becomes too big. Actually, the model seems to usually prefer blue spectrum. But for instance, I give one example that works. So if we take lambda phi to the 4, that is ruled out for cold inflation, it can give the right value. Basically, it can give you NS, which is right here, or 1 minus NS, which is 0.033, R, which is 10 to the minus 7, so unobservable. Say T over H over 10 to the 3, and gamma over h over the phi. Just as an example of how predictions for a given potential can change. Running, I haven't computed, but is, as I mentioned, it's a second order thing. It's not, most likely is not zero. It's the same, meaning that running is just suppressed, exactly. Yes, yeah. Right. Oh, okay, maybe this is, some people might care about this. The field range is 10 and plus in this particular choice. So, okay, one generic prediction of volume inflation is a small tensor to scale ratio. Of course, the other generic prediction is non-Gaussianity, which now perhaps it becomes a bit easier to appreciate because the fluid equations are just naturally nonlinear equations, right? And nonlinearity leads to non-Gaussianity. They are order 1 nonlinear, and you get order 1 FN from this system. Now I just maybe mention that there are two sources of non-Gaussianity. What is, as I mentioned, hydro nonlinearities. There is another source of non-Gaussianity, which is the noise non-Gaussianity. Because this noise is actually essentially Poisson distributed. So these are the source of this noise is actually this random local processes. So noise itself has some non-Gaussianity, but it turns out that in the end, the nonlinearities from the equations of motions are dominant because of the central limits here. So this turns out once you go to more like plug in the reasonable values, this turns out to be usually bigger. Okay, so now let me just, I'm almost done by the way. Maybe two more slides. Okay, up to here. So we expand. For this model, it turns out that two templates are relatively good to explain the full 3-point function. Equilateral plus one other shape that we call a new bar. And this new bar is actually distinct. Of course, otherwise we wouldn't introduce it. And so then the main parameter of the model is really, of course, B depends on the momenta, but also gamma over h. So this FNS depends on gamma over h in the following way. If gamma over h is less than 1, then FNL equilateral goes as h over gamma. If and this is the dominant component. So now in this regime, it's kind of degenerate with the single field non-linearities of single field models. In the opposite regime, this is something between 1 and 50 when gamma over h is bigger than. So asymptotically for say gamma over h very big, it asymptotes to something around 50. And then maybe one particular feature of the three-point function that some people care about, like for instance for a scale-dependent bias, this is the squeeze limit. When we have say K1 is much less than K2 and K3. So let me just mention that what are the general expectations. So I introduced this, let's think about this FNL function. So I normalize it by power spectra so that it becomes just a number. So this FNL function, if I take K1 much less than K2 and K3, it goes to 1 for local non-Gaussianity. It goes as K1 squared over K2 squared. K1 over K2 squared for the equilateral type non-Gaussianity. And now, if we consider warm inflation, then the FNL K1 much less than K2 and K3 would go as K1 over K2, just the first power when gamma over H is less than 1. And it goes as a constant, F0 plus F2 times K1 hat dot K2 hat squared when gamma over H is bigger than 1, but only for a range. So this is only valid if gamma over H bigger than 1, but only when okay, this, if someone cares about, probably needs to ask for more detail because this is probably not understandable. With this F0 and F2 or the 1. Okay, maybe. So basically the idea is that the behavior in the squeeze limit depends on how things behave at superhorizons, more or less. This K1 over K2 squared, it essentially has to do with the fact that the time derivative of the perturbations decay as 1 over A is squared at superhorizons. This 1 in local non-Gaussianity has to do with the fact that if there are some other entropy perturbations, they don't decay at superhorizon scales, but they are observable. So they don't decay, therefore 1. Here, K1 over K2 has to do with the fact that one of the hydrogen modes decays as 1 over A at superhorizon scales, rather than 1 over A squared. So that's why K1 over K2. Here, this gamma, this behavior, which looks like a local non-Gaussianity, has to do with the fact that actually perturbations in this regime, when gamma over H is bigger than 1, they are formed at subhorizon scale. So there is a range in which you have actually a growing mode, and within that range between, say, square root of gamma and H, still your long mode is observable. So with some amount of squeezing, you have a big enhancement, and then goes back to the usual behavior. Now, however, now maybe for more practically, what does it mean? It means that this model, effectively, when gamma over H is much bigger than 1, it looks like a local non-Gaussianity, so it gives the scale-dependent bias, right? It's called scale-dependent, the one that goes at 1 over K squared. However, it also has a quadruple component. So it's rather distinct. Now, of course, for the bias, that quadruple component is not in the bias parameters. We don't care about that because we are talking about the relation between scalars, delta G and delta matter. But perhaps if we write a bias expansion for the alignment or what is the quadruple moments of the galaxies, then this can appear. Okay, so yeah, that's basically it. This to conclude, it's interesting to have realistic targets for near future observations and warm inflation seems to be a relatively realistic target. Thank you. Yes. Yeah. Yeah, it's a multi-field model, so definitely it's not as simple as a single field, for sure. Is it obvious that the normalization happens? It's not obvious in a sense that I don't think anyone actually did a numerical simulation of that. On the other hand, I'm not originally. I guess I was also skeptical, but now I'm not skeptical at all because the thermalization time scale is all determined by the microphysics here. It has nothing to do with the expansion rate. Right, because what is the condition on thermalization? It's the fact that interaction rate you want it to be faster than the expansion rate. Now the interaction rate here is all determined by really the parameter. Say you start from 0 temperature, then your parameter is this driving force, phi dot over f. This is a dimensionful parameter. It's like a deriving force of your, as you know, it induces some kind of instability for the gauge fields if they are not populated. Like, sure, but that's because those are abelian. So here I'm saying if you start from 0 temperature, so nothing excited, it originally at linear order, it looks like 3 copies or n copies of the abelian one. So you start exciting them. And then they interact. But everything now is determined by these microphysical parameters. So the rate of this interaction, I don't see why it cannot be faster than expansion rate. But yeah, no one has done a simulation of this. I think it's an interesting curiosity to check it numerically. I mean, people do simulations of the abelian case in expanding universe, so I think it's not that far from what is being done at the moment. No. No, here there is no. In the abelian case. Sure, then there would be, then there is a question of whether you thermalize or not, how fast they distribute in the phases.